author, as you know. He has been a consultant writer for the National Academy of Sciences and National Research Council, and from 1989 to 92 he was Special Assistant for Communications in the White House Office of Science and Technology Policy. So once again, Steve.
Thank you. My intention is to speak for only about 3 minutes because there's, and I have an ulterior motive in doing that. I was going to describe some of the conclusions from my book, but this way you'll just have to all go out and read it because I'm not going to tell you what's in it. Part of the reason I wrote this book was to try to find what elements the 6 members of the IMO team had in common. In other words, I sort of started this project by saying, why these 6 kids? Out of the 15 million kids who are in U.S. high schools, what do these 6 kids have that got them to this level, this world-class level? And gradually, of course, books have a tendency to evolve. I think in the end, it's really a book about the skills that anyone uses to do anything at a very high level of performance, because the skills that the kids used in this book were skills that would be used in anything. Certainly in writing or in composing music or poetry. I mean, there are just many commonalities all across the spectrum of endeavor. So I'm going to just list the 6 categories that I came up with. The first I called insight, which I sort of took literally to mean inner sight or the ability to do spatial representations in your mind. But of course, some mathematicians use that skill to a great degree, and others don't use it at all. Some people will convert equations into geometric figures, and other people will go the opposite route to try and solve a mathematical problem. So though it's one skill people use, it's not universal at all. The second thing I talked about was competitiveness. The members of the kids on these teams are extremely competitive, and yet competition really needs to be handled in sort of subtle and delicate ways. And we heard a little bit about this morning. I quoted Melanie Wood, who's sitting here taking notes in my book, speaking about competitiveness, and she had a very interesting way of looking at it, which I wanted to repeat briefly. She says, I've always had a sort of anti-competitive position. At the training camp, there are these team contests where students work in teams against other teams. I thought that was too competitive. And in fact, for a couple of years, those competitions kind of dissolved, which was blamed on me. I didn't really have anything to do with it, but it's true that the anti-competitiveness that I tried to instill in other people was partly responsible for their dissolving. So these kids do give consideration to the sort of role of competition in these activities, and different kids have very different approaches to that issue. The third commonality I talk about is talent, what I call talent, and of course all of these kids could be assumed to have talent, and yet the closer you look at something like talent, the more complicated it becomes. Exactly what are the sources of that talent and what form it takes. The fourth element I called breadth, which was sort of this catch-all term to talk about the fact that these kids have many different skills that they bring to competitions. And of course, I'm not telling the members of this group anything that's surprising to them because you've seen all those skills. But one thing I found interesting about the former Olympians is the fact that only about a quarter have gone on to become research mathematicians. A lot of them do mathematically intensive jobs, but many of them do, they do a wide range of things once they're done being Olympians, and it sort of reflects the breadth of talents they bring to these activities. There are 2 attributes that I did find to be universal among these kids. And when I go out and talk about this book, these are the 2 points I mentioned. And the thing I found most universal about these kids is creativity, a mathematical creativity that they all share, this ability to look at problems in unusual ways. At one point I write in the book, the Olympians all had one thing in common, an amazing mathematical creativity. The problems on any Olympiad cannot be solved by plugging numbers into memorized formulas. They require sidelong attacks, inspired guesses, flights of mathematical fancy. Now I read that sentence because it's the one sentence that every reviewer quoted when they got this book, as if they couldn't believe it. They said, no, these kids have to be sitting there multiplying 9-digit numbers in their heads. I mean, isn't that what a math competition is about? And I say, no, it's the exact opposite. You've got it completely wrong. And yet, of course, it's part of the fact that people just don't know what it is when we're doing these competitions and doing this high-level problem solving. They don't appreciate the fact that it really is like writing a piece of music or like composing a poem or a short story. The 6th category I talk about in the book is called, I called it a sense of wonder, but I really couldn't come up with a very good term for it. I mean, really what I meant to get across is that these kids love mathematics, just like everybody in this room loves mathematics, and they do it not because they're being asked to or because their parents want them to, but because they really want to do it. That's something else people would ask me when I'm out on the book tour. They say, aren't these kids just being pushed by their parents? And I say, oh, no, absolutely not. You don't get to this level without having these internal sources of motivation that are extremely powerful. Two very fast points I wanted to make is there are some things these kids that they don't have, sort of the things they have in common by their absence. I mean, when you go out and look at these high-level competitions, and we've discussed this morning, you see very few kids from disadvantaged families. You see very few kids from underrepresented minorities in mathematics. My previous book is about why you would expect, biologically, to see just as many kids in high-level mathematics, and that's the subject of the book that I'm working on right now, and it just re-emphasizes the incredibly strong role of culture and the experiences that these kids have in getting them to this level. And I mean, it's something that's obvious to us as well. One final point, of course, is that we see too few girls in these competitions, and I'm sure everyone here knows has plenty of reasons for that as well. So those are the points I would make.
Thanks much, Steve. Our next speaker is Carol Blackburn, who is a research associate and counselor at the study of exceptional talent program at Johns Hopkins University.
Might need to turn on the projector, I think.
It's on, it's just warming. Yeah. No, I think it's just warming up. Yeah.
I'm a stand-in today for Dr. Julian Stanley, who greatly regrets not being able to be here. He's undergoing some medical treatment right now and couldn't leave Baltimore. But there are certain people I'll try to find that he especially wanted to be remembered to, but he wanted to be here very much and commend you on the work that you're all doing. I work at the Study of Exceptional Talent at Johns Hopkins University's Center for Talented Youth. Can you hear me? My voice doesn't carry very well. Okay. Oh, that's not doing this right. I need to use this. Okay. See if does that pick up better? Yeah. And now if I can just get, and this is the URL for the studies site. Okay, that didn't seem to do it. All right. Now some of you may know the study that Dr. Stanley began by the acronym SIMPI, the study of mathematically precocious youth, or you may know it by the current acronym, the study of exceptional talent. But they're the same SET is a continuation of SIMPI. It's just that in the 1990s we began having students join the study who qualified on the basis of their SAT verbal score as well as their math score. Dr. Stanley was the one who pioneered the use of above grade level tests to assess the ability of students who hit the ceiling on in-grade level tests. So when people say, you give the SAT to 12-year-olds, that was Dr. Stanley's idea. And indeed, the idea of giving above grade level tests to middle school students to assess where they are beyond 100% of knowledge for the in-grade level tests is something that's grown, and there are now quite a number of talent search organizations. CTY is one that covers the Mid-Atlantic and the Northeast and then the West Coast. There's another one based at Duke University that covers the Southwest, the Southeast, and there's another one at Northwestern University that covers the Mid-Atlantic. But at any rate, all of these organizations have arisen to carry on work that he began of testing students who scored in the top 3% on nationally standardized tests using an above grade level test. Dr. Stanley from the very beginning also did counseling from the students that he identified, and we've continued that by publishing a magazine, Imagine, which you can look up on the web if you'd like to. It's not specifically on math. It covers all areas of academic endeavor, but it's to help students whose needs are not met by their school resources find summer programs, activities, and role models for things that they can be doing to challenge themselves beyond school. I'm just going to give you a few numbers on this study because I think some of this will be of interest to you, may or may not be. And so this is just a really quick run through this. The other name under which you might know SMPY was the 700 Club, because it was so named because students had to score at least 700 on the mathematical portion of the SAT before age 13. As I mentioned, the study of exceptional talent now also includes people who scored above 700 on the verbal portion as well. Since 1991, through CTY's talent search, you can see that 3,885 students have been identified for this study on the basis of their math score, 1,315 on the basis of their verbal score, and 423 have scored above 700 on both math and verbal. The ratios that I show here are for the entire population, and so you can see that the male to female ratio is close to 4:1 on mathematics, whereas it's 1:1 on verbal. Some of you may also know from perhaps one of the most famous / notorious findings of the early study of mathematically precocious youth was that the male to female ratio of students who qualified at this level was 13:1. That was true for the first 3 years of this study, but here I have this broken out in 5-year cohorts, and as you can see, it's improved considerably. The first 3 years of this study were not a very systematic, we didn't cast a very systematic net. I say we, but I wasn't part of the study at the time, but that was very much a question of self-selection at that point. At this point, we're doing a much better job of reaching students in the states that CTY tests, so this is a better metric of what the male to female ratio actually is for students that score at this level, which Dr. Stanley has estimated is 1 in 10,000 in terms of mathematical reasoning ability. Just a few little things about this population. It is a population that's narrowed by the net that's cast in the first place. Students have to score within the top 3% on a nationally standardized exam in order to be invited to do this, so that we don't have students who are just going to be flabbergasted by the experience of taking the SAT, sit down to take that as a 12-year-old. But this does mean that we pre-screen for kids who do well on standardized tests. And so one of the interesting things among the students in this group, we have incredibly well-educated parents. 50% of the fathers have doctoral level degrees, and I don't have the slides for the mothers too, but only about 10% don't have at least a bachelor's degree. One thing that's kind of interesting is that there's quite a big difference in terms of the first generation effect between between the Asian and the Caucasian populations, not between the male and female populations. I'm sure that there are many more children of students from the former USSR, mainly Russia and the Ukraine, who are gifted and talented in the United States. It's just that they don't happen to come through the talent searches, in some cases because of the time at which they have immigrated to the United States. But at any rate, this is something of concern as we face perhaps changes in our immigration policies in the United States. One thing that I thought you would be encouraged by, and that's kind of interesting, is that the number of students who qualify on the basis of math has increased quite significantly over the past 25 years, whereas the number of students who qualify on the basis of their verbal score or the number that qualify on the basis of both has not increased nearly as much. Dr. Stanley is concerned that the math SAT is too teachable. So, you know, there may be a lot of kids who are doing SAT prep, but still it's kind of interesting. I would also think that the SAT verbal would be teachable too, but apparently not as many students are doing vocabulary and analogy training. Now, this is not happening because the pool that we're assessing is getting larger. The yellow line at the bottom is actually in thousands of numbers, and so the talent search pool in the states that we've been looking at has been 45 to 50,000 consistently over the same time that this has been happening. And it's kind of interesting that it's not happening consistently across the Asian and Caucasian populations. The blue line is the Asian population, the red line is the Caucasian population, and you can see that really most of that increase is among Asian students who, as I mentioned earlier, tend to be first generation, so are more vulnerable to changes in immigration policy. So the ethnic composition of the students that have qualified for the study of mathematical or SIMPI SET has actually, just completely changed over the past 25 years. I'm not saying what particularly this means, but it's just of interest to you as a community since you get to work with them. And then finally, my real motive for coming here today is that CTY has gotten a grant from the Templeton Foundation to develop a new website for the world's most, this is their words, the world's most profoundly gifted scientists and mathematicians. Actually, they said from the ages of 8 to 18, and I said, I know there are profoundly gifted 8-year-old mathematicians, but I just don't know how many profoundly gifted 8-year-old scientists there are out there. This is something that we'll be working with the other talent searches, and in fact, we're going to invite ARML and Math Counts and all of the screening organizations that already exist out there to identify mathematical and scientific talent among middle and high school students. We don't even have an URL yet because we haven't completely decided on a name. We have a lot of student involvement in the development of this project, and choosing a name is one of the things that we haven't received no one suggestion has a majority of the votes yet. But we do have an URL here, which is hard to read in this blue. cty.jhu/set/TWS, Templeton website, .html. And so that's where we'll have updates. We're certainly not in any way trying to go up against artofproblemsolving.com or MathWorld or MathForum or any of the things that already exist that serve the math community so well. But since this site is supposed to serve a broader community, we're hoping actually to learn from some of the things that have been done so well for the math community and help other students or students whose interests are not focused on math or who are not solely math. We're very much hoping that the professional communities in all of these areas are going to want to help, because we're going to be good at finding the kids and bringing them in and at setting up a framework, but we really want top-level people to be working with these students, and they're looking forward to it too. I thought I would just share with you some of the things that they said that they would like and some of the things that they're looking forward to. They are looking forward to a place where they can be just as smart in conversation as they are and not have to hide that. They're looking for a place where their age won't matter in how they're taken in a conversation. So that's something that they're looking forward to. But they've also said some very mature things like, it would be nice to not just hear one perspective on a subject. It would be nice to have a couple different or several different experts come in and talk, not a food fight kind of debate as we so often see in politics, but you know, a scholarly discussion of differences of opinion so that they can see how scholars argue. So I thought that was really quite interesting. So we're looking forward to having some discussions on the site among experts, and then discussions where kids can be part of it as well. And so, as I said, I'm very much hoping that we can use your help in whatever way you would like to help with this, and I will be in contact with many of you here about this in the future. Okay, thank you. Okay.
Thanks much, Carol.
Thanks.
Our last, with my reading glasses, where did Jim go? Oh, right there, okay. Yep, I have a little trouble seeing with my reading glasses. So our last speaker of the day is Jim Tanton. I'll just say a few brief things there. After his PhD came from Princeton, he did a number of things, ended up working for 3 years as co-director of the Boston Math Circle. He's a frequent contributor to Math Horizons, has many other accomplishments as a mathematician and mathematics educator. In the interest of time, I will send you to the website to see the fairly extensive list. Jim. What's that?
Can we bring this down by any
Sure.
chance? That'd be great. No, I'm not. I have 3 pages of notes here, and I don't think I'll use them at all. I thought, having listened to the conversations this morning, maybe a simple example is what I need to say. I've been at Princeton. I've been in the liberal arts college scene for many years. I've been with the Math Circle. I had the pleasure of working that in the Boston area for 3 years. I've done teacher training work and consulting with teachers in the Boston public school system and so forth. I decided to practice what I preach and go into high school teaching myself. I'm now at SET Math School and having a wonderful time. But I'm now a 9th grade geometry teacher. I'm at chapter 6.2 of the textbook, and I'm meant to teach this theorem. That if you take a right triangle, like so, draw the midpoint of the hypotenuse, then that midpoint is actually equidistant from all 3 vertices of the triangle. The textbook says me to do something to prove this to the kids, you know, a similar triangle, something I don't even know what the proof is. Now, I look at that and I think, what's the role of the textbook in my classroom? And I am bewildered as a mathematician. I can make my kids memorize that, they can do problems solving that problem, it's fine. And then it dawned on me, what I really need to do is this with my kids. Here are 2 dots on the board. Here's a piece of paper. Notice the corner of a piece of paper happens to be a right angle. What if I shove this piece of paper between the 2 dots? Now I'm going to play a balancing act. And suppose I mark where the corner lies. Do it again. Shove the piece of paper up between the 2 dots. Where's the corner lie? Keep doing this over and over again. I'm sure I'm not the first person to have thought of this puzzle. But if I keep doing that, what shape evolves? What curve do these dots outline? Can you say that with confidence, or are you just guessing? You're right. The kids did this. Turns out to look like a perfect semicircle. Question is, why? Well, we played around with it. We ended up drawing this triangle here. Then one kid in my class had the bright idea, well, just make a copy of that triangle underneath, turn upside down. We managed to show that it was actually a rectangle, and kids happen to know that the diagonals of a rectangle bisect each other, and they're of equal length. So is it now obvious that those 3 lengths are the same? Voila. Which of course then begs the question, well, what if my paper wasn't so nice? What if the corner were not a right angle? There we go. Start shoving that up between the 2 dots. Excuse my language. If I keep doing that, what a curve evolves then? Any idea? Try it. That is the message I want to give my kids. As a mathematician, I want to move away from the whole idea of everything is answering questions. It's actually asking questions. Asking good questions is what a mathematician does, and that's hard. And I worry about what I'm expected to do as a math teacher. It's because I have the confidence and competence with mathematics. I mean, I do have a PhD in the subject after all, that I can think of this and play with these ideas. where's that element of play in high school education? That's why I want to work in this arena. I have a lot to say, but that's it. I'm stopping right there. I'll be speaking again in session 11, where I'll probably elaborate on some of the ideas some more. But just that example, I think, says a lot. Great, thanks.
We are at lunch, which I know that you're all looking forward to. That will be on the 6th floor. We will